So we have the definition of a derivative. We're going to get into, well, what kind of notation do we have for derivatives? I'd like to get to the second day of this as well today, so that tomorrow you can work. Relationships between the graphs of f and f prime, and graphing derivatives from data, and then one-sided derivatives. I might not get to the one-sided ones. They're not that critical. But the other stuff is. What is the average rate of change of a function? It's the slope. Okay, so it's the slope. And they'll give you the endpoint, so it'll be quite obvious. What's the instantaneous rate of change? That's the slope of the tangent line. Another word for it is a derivative. And it's going to have meaning, and you are probably going to have to, on the exam, write out what a derivative might mean. And you have to be very specific. You can't say instantaneous rate of change. You have to explain what that means.
So the other order derivative.
Derivative, right. That's what a derivative is. And I just did that. I'm not sure what my graph was for. Oh, okay. Now I remember what my graph is for. That's my secant line. Let me put in, there's my function. There's f of x. And we want to call this C or A. What's your preference? C. Then we're going to go over a certain distance. Call that h. This should be familiar to you, right? Then this is C plus h. And the ordered pairs then are, this is C, f of C. So I'm just reviewing. And this is nothing new, is it? This is C plus h, f of C plus h. So that my average rate of change looks like what? It's the slope between these two endpoints. So it's f of C plus h minus f of C, all divided by the change in the x's, which is C plus h, minus C. I like to write the whole thing out because then I see the change in y over the change in x. It's kind of nice to be able to see that. Is that okay? And what's the instantaneous rate of change then? Or the derivative? What do you have to do to get the instantaneous rate of change? Right, you're going to drag that point down the curve until it comes to this point right here. So it's the limit as h goes to 0 of this expression of the average rate of change, f of C plus h minus f of C, all over h. And when we get to 3, the reason I have a smiley face on the board is we're going to find an easier way to find derivatives.
C plus C or C plus H?
Sorry, C plus H.
Oh.
Okay, so on Friday, we're going to find the easy way to do this, more or less. You'll be done with this hard algebraic way. Okay, now, we do have to worry about this. My little pumpkin's in the way, I think. Oh, it just got cut off. Is it cut off on yours? Okay, the derivative of a function, this is really important, with respect to the variable. You have to talk about a rate of change as something changes, as something else changes. And this is, by the way, now a derivative function. This is not f of C plus h, this is f of x plus h, where x is a variable. So I can find the slope of the tangent line anywhere on my curve, and I can actually find a formula. Okay, if you say that this derivative, this is one notation that we're going to use, exists, then we say it's differentiable. Sorry that the slide's cut off. Differentiable. So that means a whole lot. That means the derivative exists. And they will tell you on the exam that f of x is differentiable. You can go look at the exams, and you're going to say, oh, okay, I need to know that word. It means the derivative exists. And if you think a little bit more, if the derivative exists, then that means the point has to exist. So what does, can the function be discontinuous, or does it have to be continuous? It has to be continuous. So when they tell you a function's differentiable, they're also telling you not just that the derivative exists, but f of x is also continuous. And remember, we have three things that happen when we know functions are continuous. Do you remember them? The limit as x approaches some value, call it c, of f of x, has to exist. What else has to happen? The point has to exist. That's all they're saying, is when I say f of c exists, it's just saying that c is in the domain. Nothing fancier than that. But that's not enough, because the limit might exist, the function might exist, but they have to be the same. And so from this last line, I can actually get an equation I could use to maybe find out some information about the function. Which makes me think we should do that one too. We have lots of activities in this unit. It's a very long unit. And we'll break it halfway through the chapter. Okay? So I know it's going to be hard for you to remember, but when you know it's differentiable, you also know it's continuous. Okay, the derivative of the function with respect to the variable x looks like that. I guess I have two slides. Let's do the problem. Do you have that same problem? X cubed? Okay. Oh, we did that. You did that in your lab. This should be easy. But let's do it for the function. So it's the limit as h goes to 0. I don't want to do f of c. I want to do f of x plus h minus f of x all over h. Okay, so f of x equals x cubed. So it's the limit, and it's not right without the limit there because that's an operator. And I'm going to substitute in x plus h cubed minus x cubed all over h. Remember how to cube that? Pascal's triangle? And that math tells you what to do. I don't know what to do. I could substitute h in, but I'm going to get 0 over 0. So I don't know what to do with that unless I expand it out. That's the only thing I can think of to do. So it's x cubed. What's the next coefficient going to be? Do you know? 3. The x's are going down. The h's are going up. 3, and then x's go down, h's go up. The exponents have to add up to 3 because we're cubing. Plus h cubed minus x cubed all over h. So what's going to happen to the x cubes? They're going to cancel. I promise you, they're always going to cancel. Whoops. So what am I going to get now? Whoops, sorry. I want the limit as h goes to 0, and I end up with 3x squared h plus 3x h squared. You should have h's in every term. And how am I going to reduce that? I'm going to what? Factor it. I'm going to remove one of the h's. I'm going to factor it out. 3x squared plus 3x plus, whoops, there's an h there, plus h squared. And now we're going to do the calculus as soon as we reduce this. What happens? The h's cancel out, and now the calculus is putting in 0, and I end up with 3x squared. F of x, this is f prime of x, and f of x was equal to x to the third again, sorry. And I'm going to tell you that if f of x is equal to x to the 4th, I should get this derivative. And you'll be able to do this on Friday, maybe sooner. Right now you have to use the definition. Some of you may see the patterns. Then the next question is why. Okay, derivative, there's another form we can use for derivatives. Yes?
Can you put the 0 for x?
H. H is 0. Now, there's an alternate form for derivative at a point. And actually, in physics, this is the one that I do. So here's my function. Here is a. And then we're going to go over to some value. Let's call that x. Then what's this ordered pair? a comma, and then this is f of x, of course. Then this is f of a. Then this ordered pair is x comma f of x. How do you find the slope of the secant line there? I did that. What's the slope of the secant line? I think this is easier. It's f of x minus f of a, right, over x minus a. I actually can see slope there. Change in y, change in x. That's why I like this. And the instantaneous one, we're going to take the limit. It's not h going to 0. What's happening to x? X is approaching a. And if you think about it, it's exactly the same as the other one. Because if this distance here is h, then a plus h is equal to x. If you put that in here, and if I put it in there, then what do I have? I have the limit. I'll get to the bottom of that in a second. And it's f of x, but that's f of a plus h, minus f of a over x, but x is a plus h, minus a. And if x is approaching a, h has to go to 0. So it's the same. It just looks different. And the one I always use in physics was the top one there, not the bottom one. It's only in math class we do that. You'll be more comfortable with the a's, with the h's, because that's what we've done. Okay, notation. We can do y prime, or you can do f prime of x. And when you're in a hurry, that's a nice way to do it. But the problem is you don't see what's happening in a derivative. Now, we say the words dy dx. That's how you read that. But honestly, you should really say the derivative of y with respect to x. So what it's saying is if I have a curve here, if I change my x's a little bit, how do the y's change? You go a little bit over, the y value changes. So when you do a derivative, it's comparing how this function changes if you change the x. That's really important to understand. So I will say it over and over again. What's nice is it gives you both variables, and it uses this notation with the d for the derivative. It's Leibniz's notation. And that's the most common notation that's around. It allows us to do some other things in January when we do antiderivatives. You could talk about the derivative of f with respect to x. It's the same as this one, really. And then this is an operator, like an adding sign. It means find the derivative of this function with respect to x. So if I had the volume of a balloon is 4/3 pi r cubed. I've changed the variables on you. And if I am blowing up the balloon, okay, that's my balloon, it's not very good. Okay, if I change the radius, what happens to the volume? It changes, right? So I want to see how the volume changes as I change the radius. That's what that means. That's what a derivative is. It's how something changes as something else changes. It's not just the numerator there. It's the whole thing. Okay. That is day 1. But we might as well go ahead and get day 2 done as well. And it's the same as 2-4. You're going to be finding derivatives. Yes?
There's like an example to use the other.
Oh, yeah, we didn't do that. Let's do that. That was the square root? Okay, so let's do f of x is equal to the square root of x. Let's draw the picture first. And all we're doing is finding the slope of the tangent line. Now, you should know square root looks like that. It does get infinitely large. Not very fast. Logs are even worse. They go even slower. Okay, and we're going to take a point here, and we want to use the alternate definition, which is a, f of a, and then we'll take another point over here, call it x, f of x. The algebra is what's different with the other form. And in the homework, they'll say use one form or the other. Okay, so I want the limit as x approaches a, and I want f of x minus f of a all over x minus a. There's the formula. And you may see that on the exam, and they're not expecting you to take the limit. They're expecting you to recognize it's a derivative. So f of x was equal to the square root of x, right? Square root of x minus the square root of a over x minus a. Why did we practice these limits? So we know what to do right now. Do you remember what to do with that? I don't like that square root there. If I substitute in a, I get 0 over 0. And square root of x plus the square root of a. It's just an algebraic trick. It may not even do me any good, but I believe it will. Square root of x plus square root of a. And when you multiply the numerator out, you FOIL that, what are you going to get? You're going to get x minus a. So it's the limit as x approaches a of x minus a. And in the denominator, I have x minus a. I know you want to multiply that denominator out. Don't. Because what's going to happen to the x minus a's? They're going to cancel. And what's still in the numerator? 1. So then I'm going to get the limit as x approaches a. Oh, I just have to substitute that in. Well, let me write it out. The limit as x approaches a, it's 1 over the square root of x plus the square root of a. And when I substitute in a, it's 1 over the square root of a plus the square root of a. That's a fine answer, by the way. If I want to simplify, it's 1 over what? 2 square root of a. It doesn't matter, though. Either answer is okay. Because x approaches a. So this is what you substitute right in there. So it gives you the other form of a derivative. Maybe I'll do 2 videos. That may be too confusing. Okay, so I'm going to pause this. Bring up. So what the second half of this section talks about, finding relationships between the graphs of a function and its derivative, and graphing the derivative from data. You will very rarely get information about the function. You'll be given information about the derivative of the function. If you're talking about population growth, that's a derivative. As time changes, how does the population change? Okay, so we're going to graph the derivative if we know a function. Now, before we do that, should we go ahead and do one on our graphing calculator? Or maybe we should do this first. Let's do this first. All you do is estimate the slope. So this is f of x, and this is x. And now I want the slope at all these places. Whoops, f prime. So, like here, at 1.5, what is the slope of the tangent line there? It's 0. So 1.5, the slope is 0. The y value is 0. What do you think? We're just going to estimate. We don't care really.
Wait. So the
Slope.
y value, or the slope becomes the y value?
That's right. So if I wrote it in a table like this, so at 0, what do you think the slope is at 0? It looks pretty steep. In fact, I'd say it's very large. Let's make it 100. And then what about at 1? Just estimate. Looks like the slope is 1. And at 1.5, I have 0. Okay? Okay. What about at 0.3? What about the slope at 3? About -2. Okay. And then it's going to actually get, maybe we should do 2. What do you think it is at 2? Negative. Maybe -1. I didn't draw a very good picture. And what happens here at 5? It's 0. All I want is a sketch. So at 0, it's going to be really big, maybe infinite. It's like a vertical tangent to me. And at 1, it's 1. So it's going to come down like this. This is the derivative. At 1.5, it's going to be 0. At 2, it looks like it's at negative 1. At 3, it's at negative 2. But then at 5, it comes back to 0. And if this is, first, if our function is a nice smooth curve, our derivative will be a nice smooth curve. I just said it's almost vertical. It could have been 4. 4 is almost vertical, actually. I just estimated. You have to look at it, because it looks like this. It looks pretty vertical there. So I just gave a guess. It doesn't matter. It's going to be really big. And it's going to come down like that. So tomorrow we're going to do an activity where you'll have to match the function with its derivative. So it'll be kind of interesting to try that. But let's look at the calculator. Oh, I like that one better, but okay, I'll use the 84. Okay, tools. There it is. And what do you think the derivative of the sine function is? Well, let's find out. It's a new function that comes from the sine function. So go ahead, and if you have a calculator, and I'll show you the syntax on this. Now, unfortunately, I'm still with the new operating system. I'm going to clear that out. Now, that's old. Okay, so I'm going to go into y equals. I'm going to clear that out. That was from our lab. And let's put in the sine function, the sine of x. Now, the big problem you have is some of you take physics. And in physics, you are now in degree mode. We have to be in radian mode. So if I go under mode, make sure you're in radian mode. And even the day of the exam, we're going to try to get around to all the classrooms. You'll be spread out. That's the problem. And, there are 3 of us, so we might be able to do it. And remind you to put it in radian mode. We definitely will the day before. But you cannot be in degree mode or everything's going to be messed up. And since this is trig, I can just zoom it trig. And there comes my nice little sine curve. Now, I know what the derivative of this is, but we're going to let the calculator do this. So down here in y2, we're going to do that n derive. There are shortcuts for those who have the new operating system. I'm going to do it the long way. Math. And remember, this little arrow here says that there's more beyond the 7. It's 8. So it's n derived. Now it's going to come up in pretty print, but it's exactly what you did with the calculator, except you're not going to put in a value. But this is going to be an x, because we want to know how the sine function changes if we change the x. Now, I want to get y1, or I could retype sine of x, but I might goof up my parentheses. So again, there are shortcuts for those who have the new operating system. But if you don't, you got to go down here under variables, go over to y variables, and I want a function. You're not going to do any of the other things, and I want y1. And we want to do it for every value x. We don't want to do it at just 1 or pi. Just put what? The shortcut would be alpha and trace. Second quit. Oops. Okay. And so we need to go down here, and I'm also going to do another change, but I want to do it for every x. Whoops. So and I'll write up the syntax for the old one, and that's x. So you're not going to give me a specific point, and then I would like to see this a little better. So if I go over to the left side of y2, see it's blinking over here, I can do a trace, a circle trace. So I'm going to go down. That's a thicker line. I could do that. I could shade above and below if I wanted to. Or I could have this little circle where it leaves the trace. And now I'm going to press graph. So here it comes. And maybe you recognize what function this is. Yeah, it's the cosine graph. So the derivative of the sine is the cosine. It doesn't make sense. I'm going to take that picture and it will draw on it. You like the little circle trace? Yes. then I'll show you the syntax. It's still done very similar, but you do in y2, y1 is equal to whatever your function is, and in y2, it's n derived, it's y1, comma, x, comma, x. So this is not a constant, it's a variable now. Does that help? And let's just look real quickly. Here's my sine curve. And I bet you could guess what the derivative of the, somewhat guess what the derivative of the cosine curve is. And let's look at this. What is the slope of the sine curve right here at pi over 2? It's what? 0. What's true about the slopes from this point up to this point? They are positive or negative? They're positive. And guess what? There's your curve. It's positive. So that's what you're going to have to do. You just basically can estimate some values. And graphing the derivative from the data. Sketch the graph of function as the following properties. Okay. Might be 3.4. Oh, I don't want to do this. Man. Okay. I'm going to cut this too because it doesn't belong there. Okay, ready? F of 0 is 0. This is going to be, this is our f prime of x. This is our f of x. So this is 0. And it says the graph of the derivative is right here. And it's figure 3.4 in your book. My function's continuous. So what's true about the slope for x less than 1? It's what? No. This is the derivative, not the function. So what's the slope equal to? It's negative 1. So I want to think of a graph where the slope is equal to negative 1. That would be y equal to what? Negative 1x. So this is the slope of negative 1. Oh, until I get to 1, right? And it has an open circle there, but we'll talk about why that's open. And then, what about for x greater than 1? The slope is what? Somebody said it. This is the slope. Remember? So I want a constant slope of what? M equals 3. So what graph is that? 3x. So if I'm going to go over 1, up 3. Over 1, up 3. And that's what the function looks like. It's probably easier to read it backwards. Now, it says it's continuous, so that dot does exist, but these are open circles over here. Why? You did the lab, why? What's true here at this point? Can you find the derivative there? No. That's why it doesn't exist.
So there's no
Not a hole in f of x, a hole in the derivative. F of x, it says, is continuous. You just can't find the derivative there. Just because the function's continuous doesn't mean you can find a derivative. But if you can find a derivative, then that means the function's continuous. You'll have to think about that. And I'm not going to worry too much about the one-sided ones, but they look from 0 from the right, 0 from the left. And I'm like if I wanted to do this. So if I want to do this but no derivative at this corner, well, let's do this one and we'll be done. So I have y equals 2x right here, and then I want y equals x squared on the left side. And it looks like this. So we have a corner here, just like we did on the last one. So how do I find the derivative? Does anybody know what the derivative of x squared is? It's 2x. I could do the work, but I don't want to. That's 2x for x less than 0 or equal to 0. Whoops. And I can easily do the derivative of that because it's the slope. What's the slope of 2x? 2 for x greater than 0. So what is y prime of 0 from the left side? It's 2 times what? From the left side of 0. So it's 2 times 0, which is 0, right? This is at 0. What about y prime of 0 from the right side? It's just like a limit. The right and the left have to be the same. What's the slope at 0 here? 2. If you think about it, this is coming in, and at the bottom of my parabola, the slope is 0. You could even just do it geometrically. Slope here is 2. These are not equal. So guess what? The derivative does not exist at x equals 0. That makes sense? So you cannot have a derivative at a sharp corner. Derivatives are always smooth. It's the same as driving in reverse and not stopping your car before you put it in forward. It's a bad thing. Same is true for derivatives. They've got to be the same. One last note. Does a function have to be continuous to be differentiable? Yes. What if a function's continuous? Does it have to be differentiable? No. Can you give me just one easy example? The one we just did, or even easier, just the absolute value of x is a problem because it comes here and it comes here. Wednesday. I'm not saying we're going to collect it. That's old. Okay? So you should, between today and tomorrow, you can be working on 3.1. Are there questions on anything you want me to look at from 2.4?
Yes.
We have time. I just got to get my book. I might need a light, but we'll see. So we got lots of different activities for you guys. Oh, why do I have 2 of these? Oh, it's different. Okay, 2.4. You're going to give me a problem. I did 2.4. Number 1.
2.4 was the one that we were working on.
That's what you were working on Friday.
Oh, will you do number 5?
I did 5.
Did you? I don't know.
Oh, you just evaluated. Those are the endpoints. You don't know how to evaluate the cotangent of pi over 4?
Wait, okay, here. Okay, so,
Just the average value. So those are the x values. Those are the t values.
yeah.
Just substitute them in and find the y values and then just find slope. Cotangent of pi over 4 is 1. Yeah. Same as the tangent. Any of these other ones? Like 29? 23. I did do that one. It's on. I did that last Friday. But how about 27? I didn't do 27. They're very much the same. Yes. Yeah. So let's look at 27. Free fall on Mars. The equation for free fall at the surface of Mars is 1.86 t squared. So that's their acceleration due to gravity. S is position. And because of that derivative notation, that's why we don't use d for distance. Because then you're talking about d, dt, and that's not nice. Okay, and it says, assume a rock is dropped from the top of a 200-meter cliff. Find the speed at t equals 1. So you have a 200-meter cliff. Well, I guess this one's harder because they didn't really give you the formula. That's how fast it's falling, or the position. So you have to start at 200 and then subtract this. So you could find out where it is at t equals 1 second. But I don't want that. I want the speed. Well, what is the speed or the velocity? Yes, the change in your distance over time. That's that alternate form of the definition if you think about it. And I want the instantaneous speed. I don't want the average speed. I want the instantaneous. So that's the limit. As c goes to 0, h goes to 0, and it's f of c plus h minus f of c all over h. In this case, it's going to be the limit as h goes to 0, and it's s of, what's my c value? You could leave it as c, but it's usually easier. It's t equals 1. 1 plus h minus s of 1 all over h. You're just going to get those points closer and closer together. So it looks like it's going to be horrible, but it's not that horrible. So it's going to be the limit as h goes to 0. Don't know why I changed it to x. And so it's 200 minus 1.86, and it's 1 plus h squared. That's the first one. Minus s of 1, which is 200 minus 1.86 all over h. What's going to happen to the 200s? They're going to cancel out, which is nice. Okay, so we get the limit. You're going to really love the rules. Negative 1.86, and we're going to square that. So it's 1 plus, middle term, 2h plus h squared. These guys went, and then it's going to be minus a minus, so it's going to be what? Plus 1.86 all over h. So the algebra is not that bad, is it? They just distribute. So it's the limit, and I knew more stuff had to go away. Negative 1.86 plus 2 times a negative 1.86 h plus h squared. Whoops, I forgot something. I forgot to multiply by minus 1.86 h squared. I still get the right answer, though. Plus 1.86. What happens to the 1.86s? They go away, right? And so it's the limit as h goes to 0. Now, some of you know this from physics. And did I make a sign error? I did. Back here, because when I multiply by that negative 1.86, I should have a negative in there. And we'll talk about what that means. 2 times 1.86, because I'm too lazy to multiply that out. And then it's 1.86 h squared divided by h. Should be getting tedious by now, right? Because, what are you going to do? You're going to factor out the h, and then let h go to 0. Negative 2 times 1.86 minus 1.86 h all over h. And the h's will cancel out. And what happens to this 1.86 h over here? Goes to 0. And my answer is a negative 2 times 1.86. Is that acceptable on the exam? Yes. I wouldn't bother trying to multiply it out because I'll probably do it wrong. I don't want to get it wrong.
Wait. Okay, so you took out one of the h's.
I factored out an h right here. And I've been doing that. That's why I said it's kind of tedious for me because I've been doing it a lot. I personally would like to just divide h into both of those. I'll get the same result.
All right.
Why is it negative? This is our velocity because we're going down. Remember, we're dropping the rock, so the velocity is less than 0. We'll hit on that a lot when we get into more of the physics problems. That's the velocity. It's down. It's down, so it's negative. Oh, I won't even be here for help tomorrow morning. I just realized that.